So our goal is to learn how to define coordinates in a subspace of Rn. Rn is a vector space. And understand how many coordinates you need for defining a subspace. And subspace includes the space itself, because every space is its own subspace as well. And we're going to give you very, very brief and rough introduction to eigenvalues. I don't want to overload you with information. I want your first encounter to be friendly, short and sweet. Once you're more comfortable, we can explore the full story of eigenvalues. Now, eigenvalues are very important. That could be one of the biggest contributions of algebra and math that we use extensively in engineering, to the point that a friend of mine, he's a mathematician, he told me once that the entire engineering looks like a giant eigenvalue problem to me. Because it's almost any problem you can reduce it to solving eigenvalue. In control theory, to find the controller that will stabilize your system, you look at the eigenvalues of the system. If the real part is negative, it's stable, and a lot of stories that you will learn in control theory. If it's discrete, digital control, they say if the norm of the eigenvalue is less than 1, then the system is stable. Now, there's a lot of meaning behind these statements, but you see that as a tool, they will use eigenvalues, and then they build around that what it implies for physical systems, right? Or in a mechanical system, your vibration, your natural frequencies that a mechanical system vibrates, that comes down to the eigenvalues of your system. But in Rob 101, we talk about the math. So today we are covering basis vectors. What does it mean to talk about the dimension of a vector space? And then what it means to say coordinates. And then a brief introduction to eigenvalues and eigenvectors. Now you remember the identity matrix. This is an n by n identity matrix. You've seen this before. We define the ith column of this matrix. For example, if it's 3 by 3, we define each column to be E1, E2, and E3. You've seen this before, and we used it in several occasions. Another example, if n is 4, you get 4 column vectors, E1, E2, E3, and E4. Okay? Now, this is general for any vector space, including Rn. Just to keep it simple and manageable, let's look into the space R2. For R2, we have E1 and E2, these two vectors. These two vectors are linearly independent, if you remember. Because if you take any linear combination of these vectors, such as alpha 1 plus E1, alpha 1 times E1 plus alpha 2 times E2, which will give you alpha 1, alpha 2 equals to 0, the only possible solution here is that alpha 1 and alpha 2 must be 0. And if you remember, that was the definition of linear independence. If there's only the trivial solution of alpha being 0. And then we made it more complicated. If it's a matrix, you would get A transpose A, determinant of that, and so on. So that was the concept of linear independence that we refer to it today frequently. So they are linearly independent. And the important property is that if you think about any vector in R2, such as x, in fact, you can write x as a linear combination of E1 and E2. Any vector in R2 can be defined as a linear combination of E1 and E2. Which connects it to the idea of a span. If all the linear combination of these two vectors covers the whole space R2, then their span is R2. That was the idea of a span. Span was a set of all linear combinations of a set of linear independent vectors. Okay? Not only you can write any vector in R2 as a linear combination of E1 and E2, but also there is only one linear combination of E1 and E2 that yields x1 and x2. Now you could come up with a proof as well. You say that, assume it's not unique. And let me show that it is unique. But the fact is that you can only have one linear combination of these two vectors. It will uniquely identify x in the space R2. So it covers the whole space, linear combination of E1 and E2, and each vector is identified uniquely. You are already familiar with this idea because you know that in a 2D space, by following each axis, you could identify a point, right? And there is no ambiguity. Whatever basically magnitude you decide to follow along each axis, that will identify a point in the plane. There is no such a thing that two points overlap with the same exact magnitude along horizontal and vertical axis. They're unique. Same true for vectors. We talked about it. So it is not very difficult for you to convince yourself that this is true. Same idea that we're talking about here. You could think about this to be E1 and E2. Then this would be x1 and x2. Now I'm going to go back to two slides that we had a few lectures ago, more than a few. It was maybe 7 lectures ago. You probably don't remember, so I have to add it here. If you remember, we wrote down a vector such as A. We just highlighted that we can write it this way as well, and it works. Algebraically, you can write it and it works out. If A is a vector in Rn, we said that we can write it as it's an n tuple, right? And we could identify it as a column vector. Now, we said that we can also write it as linear combinations of E1 to En, the columns of the identity matrix. And then when we do vector times a scalar multiplication, or matrix times vector here, which is the result of linear combination we have in this line, it looks like the identity matrix times our vector, and then it gives us the same vector. So writing in columns is the same as writing as a linear combinations of the columns of the identity matrix, right? For any space, R, N. And we know two vectors are equal if every entry of them, right? Every corresponding entries of them are equal. So then uniqueness is given by that. So the columns of the identity matrix, we called it a standard basis. But we didn't really talk about it, what it means to be basis, which we're going to talk about it today. So the same idea we talked about R2, the columns of the identity matrix of size n will give you a set of vectors E1 to En. You can write any vectors in Rn as a linear combinations of them. We get back to this. So you've seen this before, and just purely using algebra, you can just manipulate terms and see that writing a column vector is, in fact, the same thing as writing a linear combinations of the columns of the identity matrix. Let's formalize it now. Now these are things that we talked about earlier too. Now we want to formally define basis vectors and their dimensions. Now suppose V is a subspace of Rn. You probably know by now that a subspace is closed under the linear combinations of any elements inside that subspace, and it contains the origin, 0. That means that's the definition of a subspace. So V is a subspace of Rn. The set of vectors V1 to Vk, each of them is in Rn, is called a basis for the subspace V if, first of all, they are linearly independent. We do not want redundancy. They need to be independent vectors and directions. Second, the span of this set of vectors should cover the entire space. In other words, the span of the set of vectors V1 to Vk must be equal to V. So the basis will give you a set of vectors that you can combine them linearly and cover the entire space. You can go anywhere you want in that subspace using the set of bases. So that's the condition for a set of vectors that we call them to be bases. But it must be linearly independent too. Then, if we have such a set, right, a set of vectors, linearly independent, span of them covers the entire space, subspace. Then the maximum number of vectors that are linearly independent in such a set is called the dimension of V. Here K, because we said set of vectors, they must be independent, so they are all independent. And we have K of them. So you could say the dimension of your subspace V equals K. So now we finally talking about the dimension of a space. You could already guess that you know that already. R2, well, you have 2 dimensions. I can move along 2 directions. Rn, you were seeing that I have n dimensions, right? This is more general because we can talk about subspace of a set Rn. A subspace of Rn does not basically need n bases, right? So a subspace, which is a part of that, this is a subset of Rn with extra condition that every linear combination stays in, is in fact generated with this set of k vectors. As a special case, Rn is its own subspace, and the set of vector E1 to En provides a basis for Rn. So that's also true. So therefore, the dimension of Rn is what? You said it with a very low volume. Say it loud. Be proud. What's the dimension of Rn? N. Because it's generated, right, using the set of vectors E1 to En. They are all linearly independent. Therefore, following from the last note here, the dimension of Rn is n. Now, these are things that you use informally in your questions, the languages. We're formalizing it. Yeah, go ahead.
So in our case, we're supposing that E is a subspace of Rn, and the dimension of Rn is n. Does that mean the dimension of E is also n?
No, that's exactly the point here. The question is, that's what makes it perhaps tricky, because Rn is an n-dimensional vector space. Every vector in Rn is an n vector, right? Now, every vector here, v1, v2, everything is an n vector. But I have k of them. Let's say k is, let's say I'm talking about R3, and then v is, I'm talking about a set of vector v1 and v2. Now, v1 and v2 in this case are what? They are three-dimensional vectors, but I have two of them. So the two of them in the familiar 3D space, I'm going to pick E1, E2, just keep it simple, right? This forms a subspace because every linear combination of these vectors, E1 and E2, will give you a vector in the plane. That's the XY plane that you know. It's not going to move you along the third direction. So it forms a subspace of R3, that plane, okay? It is still in 3D. So every vector in that space is in 3D. Now, what's the dimension of? So now we know that, let's say we know that E1 and E2, in this case, form a subspace, right? So what's the dimension of V equal span of E1 and E2? Now, V is not equal to a set of vectors, the span of them, right? Every linear combination of them, because it should cover the whole plane. So now, what is the dimension of this set? Span of E1 and E2, going back to your question. Yeah, any of you? Infinite. No, refer to, yes, Audrey, two. Refer to the definition here. Do not listen to people outside of class. 2, right? Now, we are saying that the maximum number of linearly independent set contained in V, that set, is called the dimension of V. That's the definition, right? Now, it's a reasonable definition because you have 2 independent directions. Yeah, good.
Does K need to be less than N? Or can it be greater than N?
Right, so the fact that V is a subspace of Rn, right, it implies that at the maximum your V, your subspace, can be Rn itself, right? So then that's the conclusion that you got. K must be less than or equal to N. Because the biggest subspace here is the space itself, Rn. Okay? So the abstract version of it is a little intimidating, but it's actually, once you draw it for 2D and 3D, it is simple, it's very reasonable. So it is possible in, let's say, a 10-dimensional space to have a subspace that has less dimensionality, 2, 3, 4, whatever is the span of that subspace. So that's, hopefully you're comfortable with this idea. Then the notation should make sense. Now, I could tell you that as an informal version, just count the number of bases, that's your dimension. But the concrete definition is that you need to look at the maximum number of vectors in a linearly independent set. We don't want to upset mathematicians. But you just can count the number of vectors in your set of bases, basically, if you know they're independent linearly. Now, this brings us to something that you might have observed. I mean, what makes E1, E2 special? What makes the identity special? Or is that the only choice? Because we naturally write it down. We don't think about it much. Usually you guys are convinced, and I'm happy we continue. Then you go home and you think, was that the only choice? I should have asked. Today we're going to answer this concern. Let's see. We have a question in chat. In the example drawing, what would subspace V look like? So the subspace V in this drawing is the infinite plane that contains, the plane continues by definition infinitely, just like line. That contains vectors E1 and E2, right? With 2 vectors, you can define that plane completely. That's the shape of that subspace, right? So subspace of R3 are basically planes, because if you ever can explore 3 independent dimensions, right, then you can cover the whole space. Which brings us to this point, that it can be only do it using E1, E2, and E3, or there are other vectors we can do it.
Like all of this scalar multiples of E1 also be as far as.
Yes, great observation. That's the point I was going to make, is that can we just say any scalar multiple of E1 to be a vector that is part of the basis? We can, and we're going to go to it soon. And that's exactly the point, that you can multiply, scale them. You can rotate them. As long as they are linearly independent, it makes sense. We might not be comfortable to work with them with hand, but they are perfectly fine bases. So before that, terms that you will hear, you read in books, I might use sometimes, canonical or natural or standard basis. The familiar vectors that we use, E1 to En, the columns of the identity matrix, forms the basis for vector space Rn. These are called natural or standard or canonical basis vectors. Because it's really the least complicated way you can write it, right? This is the least complicated way. Do not scale them, do not rotate them, keep them orthogonal, right? Dimension 1, dimension 2, dimension 3. That's, you could think about it the obvious way, or standard way, without making it complicated. So when somebody in textbook you read, it says, let this set of vectors be the standard basis of Rn, right? Usually there's no more elaboration. That's just the meaning behind it. So going back to what Yash said, that I'm going to scale alpha 1. Who can tell me don't? Can you tell what's the difference here? Let's separate. This is example 1. This is example 2. So in example 1, the one on top, in the left image, I'm showing you my arbitrary choice of basis. What you see, the grid is stretched more along the vertical direction because let's say the vertical vector is twice of the, don't remember the exact number, but let's say I am using E1, or you can make it even more interesting. I'm using 0.2 of E1 and 2 times of E2. It is perfectly fine. Now, but what happens is that 1 unit in the direction of E1, it only moves you 0.2, whatever that unit is, right? And 1 unit in the direction of E2 in this set of bases will move you 2 units. So the grid is a stretch. They're not the same thing, but you can perfectly represent a point by moving along the first direction and the second direction, right? Now you might think that, why don't we call this a standard? By any stretch of imagination, I guess this is not a standard because we are not moving the same amount along different directions. That's if you want to count your steps, for example, walking, probably you want to know how much you're moving, and it's not about if I move to the right, count it twice as I move to the left, right? Or straight. It could be an application that you want to do that, right? So it is a possibility. The second example, maybe this is a little more interesting. Now my vectors are not even aligned with the orthogonal system that we usually draw. They are rotated. My vectors are rotated. This is not out of plane. This is a just the grid rotated, right? Everything is in 2D, in the plane. There's nothing in 3D here. It's an optical illusion. Basis is real. Everything else is illusion. That's what we see here. So what's the difference here? I have a point, right? I'm just following the new rotated frame, and I end up in the red dot. Important question. Can I represent the same point in the plane using any of these two, basically, definition of basis? The first one and the second one. Let's say I pick an arbitrary point here. The fact that I choose basis 1 or 2, will that change the actual location of that point? No. That's the answer I want to give, but I think you could also say yes in the sense that it depends on the observer, right? But the point I'm trying to make is that the point is not moving. Your system of measurement is changing, right? From one set of bases, you're measuring the distance relative to different directions. They can be rotated. They can have different scales. Somebody is using meters. Another person is using inches, right? Maybe you're measuring in feet. That doesn't change the fact that that point is there. Now, the frame that you choose for measurement, well, you are observing, right? So in that sense that you are observing, of course, it changes the value. But the same point can be measured in different frame of reference, okay? This conversation gets more interesting maybe in a physics course, but here we're just trying to make a point that the basis is arbitrary. And the only one we call a standard are the columns of the identity matrix, okay? Now, you might not be comfortable to do hand calculation here because you can do hand calculation. Drawing is harder, I guess. Okay, so now you know why we call them standard, because there are virtually infinite possibilities, and those are the only one that stands out because are related to the identity matrix. Now, what is a coordinate? So we want to talk about vector space coordinates and their representation. Suppose V is a k-dimensional subspace of Rn with basis V1 to Vk. Or you could also consider all of Rn. That's the biggest subspace, k equals n. Then every vector x can be uniquely expressed as a linear combination of these vectors, basis vectors. We talked about this. So x can be written as linear combinations of the basis. Now, if you stack all these coefficients into a vector, and you may choose to use this very complicated notation.
Can you just go back to the previous slide?
Going back to the previous slide. And be quiet. You forgot to say that.
So
So you have a question, or you just wanted to take notes?
Well, a bit of both.
Okay, so what's your question?
So each x within, or each x contained be expressed as a linear combination.
Okay, so first we talked about that every vector can be written as a linear combination of a standard basis, right?
Every vector can be written
E1, E2, E3. That's easy to prove. We had the remark. Then we had a lengthy conversation that, well, those are arbitrary. You could choose any vector, right? Regardless of whether it's easier or harder, you can change E1 to En to V1 to Vn. Yeah, good.
The only restriction for our basis vectors will be that they're all the same magnitude.
The only restriction is that the basis vectors must be linearly independent and their span must be equal to the entire subspace. That's all we care about, right? So E1 to En, or K, whatever is the dimension of the subspace, can be V1 to Vk. You choose a set of vectors that are linearly independent and span the whole space. So if then the choice of basis is optional, then we can write our vector as a linear combination of any vector, set of vector bases that we choose. Okay, so that's the reason now instead of E1 to Ek or N, I'm writing V1 to Vk. And of course, my vector is not just the sum of bases, but has some scale coefficients along each basis. If you stack them in a vector, alpha 1 to alpha k, this is called a representation of x in the basis v1 to vk. Now, I'm selling it to you as if this is a new thing. We've been doing this forever. This is the same thing as x. We write x as x1, x2, xn, right? So I'm simply saying that writing this vector here, x1, x2, xn, we are used to doing that because what we mean is that x is a variable, right? And we defined it in the standard basis. Now, to make it arbitrary, we need to give it a better name that covers a more general case. If it's not a variable, we just have a vector x, we know what it is, right? X, for example, we will see example 1, 2, 3. We know what it is. It is a linear combination of our basis. So the set of these coefficients, alpha 1 to alpha k, it is with respect to this set of vectors, this basis. So it is a representation of x in the basis v1 to vk, right? So it matters what, now it matters what basis we are choosing to represent our vector. So these alpha values are called the coordinates. So when you hear coordinates, coordinates are these coefficients. They can be related to any optional basis. What makes coordinates convenient? The fact that you can use different directions and work with them. We love them in engineering. The traditional math is based on that. And this is still what we use. What we don't talk about is in modern mathematics, they do a lot of things coordinates free because, well, if it's arbitrary, we may work in a system that we don't have to define coordinates, but we can when we need to. That's not really embraced by engineering yet. Next century, maybe. At the end of the course, I'll share a book with you. It's using exterior algebra. It is very scary. Luckily, maybe 100 years from now, Rob 101 will be in exterior algebra. We're good for now, but it's coming. So the modern mathematics has developed coordinates free. But coordinates are very convenient in engineering. That's the standard way of solving problems. So coordinates are with respect to a basis. And when you show a vector in that basis, that's basically a representation of that vector. So what's nice about the standard basis? Say it again.
Alpha can be any value.
So we can drop all these nonsense and just don't talk about it, right? In that sense, it is the canonical way. It is the default way of thinking about it because we don't have to talk about these things, right? But the fact that this is possible, it will lead to important problem later. Is there any situation in life that we do not want to use a standard basis? Yes. And that will be motivation for eigenvalues and eigenvectors. There are motivations. If you have a rigid body in mechanics, your standard basis might not be a set of axes that defines the symmetry of the object. The mass is distributed in a symmetric way, right? Finding the set of vectors basis that the mass and inertia is distributed in a symmetric way, that's a problem that you want to solve because then all your calculations are simpler in that frame. Then it will actually be so much harder to work with the standard basis because your mass distribution is uneven. Okay? If you write down the equation of motion of a gyroscope can spin in 3 independent directions in space. It's a mass. Then probably you'll be pleased to see it in the principal coordinates is attached to the body that defines the mass in a symmetric way. Otherwise, you get a lot of extra terms in your equations, and they're not fun to work with. So it happens a lot in real world. All right, so a lot of nonsense to just talk about a vector and its entries, to just keep you conscious of things that we took for granted, basis, directions in the space. And I think I mentioned it verbally that the k-tuple alpha, these are called coordinates of x. So each alpha is a coordinate associated with this particular basis. Let's look at an example. Now consider a subspace of R3. The subspace is defined such that you have 3 vectors, x1, x2, x3, such that the sum of the entries of your vector equals 0. Now you need to, of course, show that this is a subspace, but the question is telling you this is a subspace. As an exercise, you can verify that. You can easily check that it contains 0, right? The origin. And then you need to show that every linear combination of vectors here is also part of this subspace. And you can do that, right? It will end up being just redefining each x1, x2, x3, and it will be a subspace. Yeah, go ahead.
Just say that
It is a plane, right? Yeah, because a plane equation, we talk about it later because we're not really, I use it sometimes, but we're not talking about geometric objects here. But this is an equation of a plane, ax1 plus bx2 plus c, x3 equals d, right? So generally speaking, that gives you a plane. We will have a lecture to talk about hyperplanes and how they use the machine learning for classification. Now, show that v1 and v2, these two vectors, is a basis for this subset, and that V is a two-dimensional subspace of R3. In addition, we want to show that this vector V is in V, and we want to find its coordinates. So, a lot of things to do. Let's see. To show that a set of vectors, V1 and V2, is a basis for V, we need to check, first of all, it is a subset of V. That means these vectors are part of that space to begin with, right? Then we need to show that they are linearly independent. Then we have to show that the span of these two vectors equals the subset. We need to show these three steps. Then we can say this set of vectors, V1 and V2, is a basis for V. Okay, so now I leave it for you to check that V1 and V2 are given, right? You just need to plug in the numbers and check that whether they belong to the set V or not. They do belong. And they are also linearly independent. If you remember, you could stack them in a matrix, right? A, take A transpose A, take the determinant. If it's not 0, they are linearly independent. You can do that. So the hard part is showing that the span is the entire space right now. The first two parts are true. I leave it for you as an exercise. Okay. Now, to show the span property, let's start from the definition of the subset. It's telling us the sum of the entries should be 0. You can find one coordinate based on the other two. It doesn't matter, right? Here I choose x3 according to x1 and x2. It's going to be negative of some of them. So my vector actually can be defined completely by x1, x2, and negative of x1 plus x2. Okay, so now, so every vector in this subspace has this form. If I take x1 and x2 to be 1 and 0 respectively, I will get v1 back. If I pick x1 to be 0 and x2 to be 1, I get v2. V1 and v2 are given as vectors. You can go and check the numbers. A particular choice of x1 and x2 can reproduce those vectors. Okay. So the span of this set is in fact the entire space, because if you pick V1 and V2 that we just confirmed they are in the space, right? We just confirmed that V1 and V2 both are in the space. So take x1 times V1 plus x2 plus x1 V1 plus x2 V2. Definition of the span tells us that the linear combination should cover any vector, right? Now, what you don't see there is V1 and V2. x1 V1 plus x2 V2, right? Should have added them to remind you. Is x1, x2 minus x1 plus x2. So the linear combination of V1 and V2 is giving us exactly the definition of the subspace. So it is the span of V1 and V2 is the subspace. Okay? That's how we are showing it. To recap, we showed that V1 and V2 belong to the space, and the linear combination is in the general form of any vector in the subspace, which is this. So the dimension follows from the number of elements, which is 2. Right? We have V1, V2, linearly independent, so the dimension of the subspace V is 2. You can use this notation to say that the dimension of V equals 2. Question is asking more. We're saying also, check if this V is in the space, right, in the subspace, and then find its coordinates with respect to the basis V1 and V2. To be in the subspace, we need to show that sum of x1, right, plus x2 plus x3 will be 0. It is 0, and this vector belongs to the subspace. Okay? Now that it's in the subspace, we can talk about its coordinates. Now, the vector, the coordinates that you see in V, right, those are in the standard basis. What you see here, be careful, this is in the standard basis. The question is asking its coordinates with respect to the basis V1 and V2, right? To find the coordinates of V in the new basis, V1 and V2, we need to write it as a linear combination of these two vectors. And we know that we can do that because their linear combination spans the entire subspace. You can show that 3 times V1 minus 4 times V2 will give you V. So the coordinates are 3 and minus 4. So the vector is 3D, the subspace is 2D. Using 2 coordinates, right, we can show this 3D vector in an arbitrary basis of V1 and V2. This is a concrete numerical algebraic example of those figures. You could choose any basis, you could represent your vectors, you can find its coordinates. This is basically your alpha 1, alpha 2, right? Now let's go back to matrices now. Suppose we have an n by n matrix A. The following statements are equivalent. You can talk about the determinant is not being 0, which we know that means the columns of A are linearly independent. What we didn't talk about, and we can talk about it today, is that this is also equivalent to saying that the columns of A form a basis for Rn. Because the columns of our matrix are linearly independent, and our matrix is n by n, right? So we have n linearly independent vectors. It can form a basis for Rn. So any n by n matrix that is not singular, the determinant is not 0, can span its columns. The span of its column space is the entire Rn, right? Another way to say this is that your matrix, your n by n non-singular matrix, can take any vector and turn it to any other vector in Rn, because it spans the entire space. This is not always possible, because the columns of the matrix should span the entire space. Must span the entire space that you can do that. So a special case is when your n by n matrix is the identity matrix. Then we know that the columns of A are your familiar canonical basis. So everything goes back to matrices again. Those bases and vectors forms a matrix, and you can think about it as a transformation, basically. And when you multiply your matrix by vector, you are essentially writing linear combinations of the columns of your matrix in coordinates. We always talk about new things and we go back to same thing. And hopefully that's a good thing, because we're going to have a recap next week maybe to reiterate what's important, what we really should remember. There are a lot of equivalent things we're saying. We want to do a recap to make sure you remember the important part. Example. Determine if the set of vectors v1 to v5 form a basis for R5. What should we do? Space is R5, and I'm giving you 5 vectors. I would like to know if they form a basis for the entire space.
So what do you mean figure out if they're linearly independent?
Yes, we need to figure out if they are linearly independent. And the easiest way is to form a matrix, right? Arrange them in the columns of a matrix. Go back to your Julia notebook, calculate the determinant of A is 16. Then we know that they're linearly independent, and therefore the set does form a basis for R5. And it's very different from a standard basis, but it spans the entire space. Yeah? What about rectangular matrices? Then those are subspaces. This is as good as it gets. It's a 5-dimensional space, R5, and we're giving you 5 vectors, they're linearly independent, so it covers the whole space. You could talk about a subspace that is 4-dimensional, right? Yeah, go ahead.
So I thought it has to satisfy 2 conditions for it to be a basis. I thought that you wrote that it has to be linearly independent, and the span of it is also have to equal the A. Am I wrong?
To be a basis, it needs to be linear. They need to be linearly independent, and their span must be the entire set.
Or are they mutually inclusive?
It is, because you have 5 vectors, right?
Yes.
If you have 4, then it's not. Remember, for Rn, we need n linearly independent vectors to span the entire space.
Yes.
So that condition is because to be a basis for a subspace, you need, at the very minimum, you need the same number of vectors as the dimension of that subspace, right?
Yes, but how can you say that this is a basis for R5 if you didn't test for the span?
Because each vector is 5-dimensional, and I have 5 of them. So I can write any vector in R5 as a linear combination of them, right? We go back to your question is, how do we know that's for R5?
Yeah.
I think we talked about it somewhere.
So the dimension, or are you saying K has to equal N?
Yeah, that's exactly. So to be a basis, right? This is what you mentioned yourself. They need to be linearly independent. We verified that with the determinant. But also the span must be the entire set. Now, if I'm talking about Rn, right, K must be equal to N. Because each of them, Vi, is an N vector. Then I need N of them. So my matrix must be square. It cannot be rectangular, right? Does that make sense? Yeah.
The equivalence principles where the determinant of A is not equal to that one. Does that only apply for when K is equal to N?
The equivalent that, can you please repeat it? Yes, the equivalency means that you can use any of them. The easiest, I guess, is to form A and take the determinant.
So that only applies though if it's a square. Or if K is equal to N.
Yes. Yes, because I should have drawn a thicker line. So, yes, good observation. When we talk about determinant, it must be a square matrix, right? We cannot talk about determinant of a rectangular matrix. This is a more specific topic, columns of a matrix and basis of Rn, right? If it's n by n, non-singular, the columns cover the space, right? I think that's the point I'm trying to make here. The general case when they're rectangular, it's not going to be like that. First of all, there is no determinant. Then we have to talk about subspaces, right? And you cannot have 3 basis vectors in a 2D space, right? That's just not possible. The biggest subspace is the space itself. Okay, so this is a more specific point that I'm making here. But your takeaway here can be that think about a matrix as a transformation. Its columns can send you anywhere in the space if they are basis for the space. Again, this we talked about. This is a very advanced way of thinking about a matrix, a map, a transformation. You use linear maps in your first project. That's the same idea. Matrices can translate, can rotate, can scale. These are all properties that you can gain from your matrix. For example, if you constrain your matrix that, say, your matrix cannot scale, it must preserve the length, right? Then it is more special. It's not anywhere. It cannot send you to twice of the initial vector that you had. Maybe it can rotate it, maybe it can translate it. That's going to be all you can do. So the last topic that I'm going to briefly cover is just the concept of eigenvalues and eigenvectors for today. Eigenvalues are only defined for square matrices. You cannot talk about eigenvalues of rectangular matrices. There is another general concept. It's called singular values. In a sense, it's a generalization of this. So only square n by n matrices have eigenvalues. Let A be n by n real matrix. That means every entry in the matrix is a real number. Because it's also possible to talk about a matrix that has complex entries. There is nothing wrong with this. You can do that, right? Now entries of a matrix are complex numbers. Now the full story of eigenvalues need complex numbers because they can be complex too. Today I'm just going to talk about real. Later we should probably cover more on it. So when I say let A be a real matrix n by n, I mean not this. All of them are real numbers. An eigenvector V satisfies, eigen is a German name. It's coming from German math. It means, I think, self or own, something like that. We'll see why. So eigenvector V satisfies your matrix times V equals just the scalar times your vector. And that scalar calls eigenvalue. So whenever lambda is not 0, such that the span of your matrix times your vector, which is a vector, right? Is the same as the span of V. That means multiplying your matrix by V, it will not change its direction. It will only scale it by lambda. Sounds crazy. And it is. How is that even possible, right? You multiply matrix, the giant matrix, all those numbers going left and right, you calculate. All that happens is that the scalar times your vector can define that. Is that even possible? Who thought about this first? Of course, a German mathematician. They kept the name. I mean, numerically, let me prove it to you that this is possible, first of all, right? I'm giving you a matrix A multiplied by vector v1, v2, v3. See what happens. When you do that, A times V1 will give you 2 times of V1. A times V2 will give you 3 times V2. You can verify this, please, in Julia for yourself. A times V3 will give you 4 times V3. It works, so it is possible. This is like a forward way, verification way. Our problem will be finding out what are these eigenvalues. How can we find out about them? So a matrix multiplied by that particular direction only scales. So your matrix A acts on this set of vectors, it only scales them. In other words, there is no rotation when you multiply your matrix, because if you draw your vectors, right, in, let's say, 2D, you multiply a matrix, you draw the new vector, it's probably somewhere else in general. Change of rotation in the sense that the direction will change, right? It's not happening here. It is only scaling. It's very, very surprising and special. This is the topic of eigenvalue and eigenvectors. So if this happens, then V is an eigenvector and lambda is your eigenvalue. If this special case holds, we call lambda eigenvalue and V eigenvector. So a temporary definition, this is not the full story because we're talking about real cases. Things are more complicated than they seem. A scalar lambda is an eigenvalue of A. If there exists a non-zero V, V should not be just a zero vector, such that we have A times V equals lambda times V. We call V eigenvector and lambda is eigenvalue. Now, it is important to note that A times alpha times V equals lambda times alpha V, right? So you can get rid of the alpha. So any scalar multiple of your eigenvector is an eigenvector. They're not unique. It's the direction that is important. Because two sides of the equality will cancel the scalar. So, but lambda, alpha cannot, the scalar multiple cannot be zero. So to find eigenvectors, we care about the direction. The particular scale of it is not that important. It could be normalized too if we want to. A lot of time we do, but they don't have to be normalized. So to find the eigenvalues, so that special property is very interesting, and then the question is, how can we find them? I give you a matrix, find these scalar, special scalars, eigenvalues and eigenvectors that collapse the matrix when you multiply it by vector, it's only scalar in one direction. So let's start from A times V equals lambda times V. Move everything to one side. We're working with the n vector here. So right-hand side will be 0, n by 1. Now I hope you're comfortable that lambda times V is the same thing as lambda IV, right? Because we talked about it. Identity matrix times my vector is actually its natural form. But you could just also add this because it doesn't change anything. So we add the identity and then we factor V from right. What we're left with is that lambda times identity minus A times V equals 0. This looks like a homogeneous system of linear equations. And it is. That's what we saw. I mean, we used to see ax equals 0, but here we're talking about lambda I minus a v equals 0. V and x just variables, it doesn't matter. This just another matrix, a new matrix. But lambda is also variable. Now, note that if v is not 0, the only way there's going to be a non-zero vector, right, solution of homogeneous system of linear equation is that the determinant of this matrix is 0. That means there should be some non-trivial solution. Remember, a times x equals 0. The obvious solution, the trivial solution was x equals 0. The only way we could find out other solution was when the determinant of A, right, a square matrix, was 0. That means the columns were linearly dependent. That was bad at that time, but here it's to our advantage because it must be the case, and we can play with lambda, find lambda such that makes this lambda I minus a singular, collapses that to one particular direction, and that will be our solution. If you remember the null space that we talked about, in other words, V must belong to the null space of this matrix, lambda I minus a. V is in the null space of A. No, not A. Lambda I minus A. Making it a little fancier, you can say that. So the two, and the determinant of lambda A minus A equals 0, this will lead to usually a polynomial equations. That's called characteristic polynomials. We solve that polynomial, you find eigenvalues. Let's see. I give you a 2 by 2 real matrix. Find its eigenvalues and eigenvectors if they're available, if they exist. They always exist. It's by our definition of existence, real. What is, first of all, this whole matrix here is lambda times identity minus a. Lambda will always appear on the diagonal because lambda times identity will be just a diagonal matrix, right, with lambda on its diagonal. Subtract a from that, you get this matrix, take its determinant, it's 2 by 2, so it's going to be lambda A, B, C, D. You remember it's going to be AD minus BC. A quadratic equation. You can solve it by hand or Julia. You will find out that particular values of lambda equals -1 and 4 are such that will make determinant of lambda I minus a to be 0. Then there will be null space for this, right? This particular choices of lambda will do that. To find, now, for each eigenvalue, we're going to find one eigenvector. They come together. For each eigenvalue, you have eigenvector. To find the eigenvalue associated with lambda 1, we start from the same equation here, but instead we work with the numerical value of lambda 1. Evaluate whatever is here. What you get is here a matrix times a vector v1. two components. I'm calling it A and B. Now, what is vector V that will satisfy right-hand side, make it 0? Any vector that has this form, alpha 1 minus alpha 1, right? Again, the scalar multiple of that vector is not important. Any vector that is 1 and minus 1 will satisfy this equation. So that is my eigenvector. In other words, lambda A times V1 equals lambda 1 times V1. Now I have one eigenvalue and one eigenvector that satisfies this surprising equation that only scales the vector. So I found the direction, actually. For different matrices, these are different, right? So eigenvalue and eigenvectors are